Hello everyone. In the lecture today, we will learn some basic concepts of measurements, which will be the most important term in this class. And then we will identify the measurement errors, including its cause and the potential strategy to remove the errors in the measurements. First, we need to define what a measurement is. The measurement is an act of determining the weight, length, capacity, size, or other dimensions such as force, acceleration, and so on the aspect of the physical universe. In order to have a meaningful measurement, we need to use instruments. And the quality of the instrument is very important for us to determine how good the measurement result is. With the higher quality of the instrument, the uncertainty within the measurement would be smaller, and this will give us better measurement result. There are some standard procedures for us to use the instrument to conduct the measurements. Here, let's take the length measurement as one example. First, if we want to measure the length of one object, we have to set up the tape and stretch the tape with the appropriate force. And then we will align the zero mark to the left end and observe the readings on the tape at the right end. The reading from the tape is just the length measured by the tape. In the previous example, we mentioned the observation for the length measurement. And actually, observation is a very important concept for surveying. The observation is the value read by the surveyor from a manufactured tool. Usually, the observation is different from the true value, and this difference is caused by the uncertainty of the surveyors or the mistakes of the instrument. To quantify this difference, we define the error. It is defined as the difference between the true values and the observation. There are many types of the errors in measurement. The first type is called a gross error, and this one is also defined as mistakes or blunders of surveyors or the equipment. It's usually caused by the carelessness of the surveyors in the experiment, or the failures of the equipment, or misinterpretation of the surveyors to the observation. In order to remove such errors, we need to take multiple independent readings and check for reasonable consistency of the observations. Also, we have to use some simple and quick technique for verification in the field experiment. If you find any error, you can quickly repeat the experiment and get a new observation. Also, you need to check and verify the performance of the equipment before you conduct any experiment. Repeating the experiment is very important for you to remove the gross errors. Also, you have to increase the number of the observations even for a single experiment so that you won't have affected by the mistakes. The second type of the error is called a systematic error, and this one is very different from the other types of errors. Systematic error has a well-defined pattern which can be mathematically described, and you can repeat the error at different experiments. Usually, this type of the error is caused by the natural environment, such as the temperature and lighting conditions. It could also be the problem of the instrument or the limitations of the human observations. There are two terms for us to identify systematic errors: correction and residual. To define correction and residual, we need to first check a set of variables. XC represents the corrected or the true value. ES is the systematic error. Letter X is the observed value. C is the correction, D is the residual, and X hat is the estimated value. First, for the systematic error, ES equals to the observation minus the corrected or the true value. Then with this one, we can define the correction as minus ES. So with this one, you can see that the true value is the observation plus the correction. And last, for residual, it actually represents the difference between the estimated value and the observation. Also, we will have x hat as x plus d. The third type of error is a random error. It represents error or observations after all mistakes are detected and eliminated, and all sources of systematic errors are identified and corrected. So usually random error does not have any pattern and is a random variable. In random error, we have to consider the discrepancy about different observations of the same measurement. Assume that x1 is observation number 1 and x2 is number 2, then discrepancy dc can be defined as x1 minus x2. Here we specify that random error is a random variable. So in order for us to remove the impact of the random error in the measurement, we need to know what a random variable is. Random variable is a variable that takes on several possible values and probabilities is associated with each value. So here we have a new term, probability. The definition of probability is a little bit complicated here. You can go through the sentence below. But to make it simple, the probability represents the chance of success under a pool of options. Now let's see one example about the random variable. In this example, we will flip a coin for 100 times, and in the 100 times experiment, we find 53 times with the front and 47 with back. With this information, we're able to define the probability of front as 53 over the total number of times as 0.53. Similarly, for the back, we will have the value as 47 divided by 100, 0.47. In addition, you can find that if you sum these two probabilities, the probability of front plus the probability of back is always 1. So this is actually one important feature about the random variable. The sum of the probability of all possible values will always equal to 1. For random variable, we also have some other important terms. The first one is called population. It represents the totality of all possible values of the random variable. And the second one is sampling, which means the samples that we draw from the population. For sampling, there will be some statistics for us to represent the features of the data, including the histogram, location, and dispersion. Now let's see how we can use the histogram to represent a sample. The table here shows the height of 20 students, and we want to draw the histogram about these 20 students. In order to draw the histogram, you first need to specify the range of all the possible values for the sample. In this example, the student height varies from 160 to 190 centimeters. We should use the bins to cover this whole range. Next thing, you need to choose an appropriate bin size. In this result, we actually choose the bin size as 5 centimeters. So for the first bin, it represents the height from 160 to 165. Second one is 165 to 170, and so on for the rest of the bins. The next step, you're going to try to count how many students' height will fall in each bin. For the first one, we observe that there are 2 students with their height between 160 and 175. You also can try to count the number of the students falls in the other bins. When you identify the numbers for each bin, then you will have the histogram. This is the way for you to do the histogram by your hand. You can also use Excel to generate the histogram automatically, or you can use some other programming languages such as MATLAB or Python. Location is another feature of the sample. Usually there are two types of the variables to identify the location of the sample. The first one is mean, which means the average value of all the samples. Assuming that there are n observations, x1, x2 to xn, then the mean will be x bar. That will be the average value of all the n observations. So you will have x1 plus x2 plus until you go to xn over the total number of observations. And you can also simplify this one as a summation of I from 1 to n for xi. Now let's go back to the student height example to see how we can calculate the mean of the sample. We know that in this example there are 20 students, so capital N will be 20, and then we can call the formula of mean to determine the average value of the student height. That will be the summation of I from 1 to n xi over n. We know n is 20, so summation of I from 1 to 20 xi over 20, which will give you the value as x1 plus x2 plus xn, and xn here is 20 over 20. And we should put all the student height information here. The first student, the height is 179, and second one 167 plus all the other students. The last one is 178 over 20, which will give you the mean as 174.7. So that's the way for us to calculate the mean. The second type of location is called a median, which represents the median value of the set of observations. To identify the median, we should first sort the n observations from low to high. If the total number of observations capital N is odd, then the median xm will equal to the half n plus 1's value. And if n is even, then the median will be xn over 2 plus xn over 2 plus 1 over 2. That will be the average value of the two observations in the middle. And let's take a look at an example of the student height. In order to find out the median of the student height in the class, we should first sort the n observations. So we know capital N is 20, and then we have to find out the 10th and the 11th observation. The reason for us to choose these two observations is that n is actually even, so we have to call the equation of x n over 2 plus x n over 2 plus 1 over 2. And based on the sorted student height for the whole class, we can get the median as 175 for the 10th student and 177 for the 11th, which will give you the value for the mean as 176 centimeter. So that's the way for us to find out the median. The first step is very important. So you have to sort all the observations first from low to high. The third feature of sample statistics is the dispersion. It measures how far the observations are from the mean of the sample. Usually it measures with the sample variance and the standard deviation. The equation here shows the formula to calculate the sample variance. For sample deviation, it's usually the square root of the sample variance. Now let's go back to the still and high example for the calculation of the variance and the standard deviation. First, we need to list all the information we already got. We know there are 20 students and the mean of the sample is 174.7. And now first for the variance, let's call the definition of variance. We have S squared equals the summation of I from 1 to n xi minus x bar square over n minus 1. In this example, we have capital N is 20, xi minus the average 174.7 square over 20 minus 1. And then you apply all the values in the table. For xi, you will find out the variance as 61.21 centimeters, actually square. For the second one, standard deviation, which is just the square root of the variance. That will give you the value as 7.82 centimeter. So that's all about the sample statistics. The next thing we need to think about is the quality of the observations. In general, the quality is measured by 3 variables: resolution, precision, and accuracy. First, for resolution, it's related to the smallest division of the actual reading that we can take from the instrument. That means it's the feature of the instrument. Usually we treat the digital instrument and analog instrument differently. For digital equipment, the resolution is the smallest division from the instrument display, while for analog, the resolution is the smallest division which can be taken reliably. Usually the uncertainty due to the resolution is half of the smallest division that can be read from the instrument. For precision and accuracy, it could be easily understood. Precision indicates whether the observations are concentrated to a value. Accuracy means whether the observations are close to the true value. Precision actually measures how much does the repeated measurement of the same physical quantity varies around its average value. So if the measurements are very close to the average value, then it means that the measurement is precise, otherwise it's imprecise. In general, precision is related to random errors, and it may cause inaccuracy in measurements. Usually it's very difficult or almost impossible to be identified with a very small number of data points. So in order to know how large the random error is, we have to repeat the same measurements for a lot of times. Usually the precision has a very significant impact to the overall quality of surveying job. Another thing we have to pay attention is that precision is very different from resolution based on the definitions we specified in the previous pages. But in reality, a lot of surveyors are confused about the precision and resolution. So we should clearly know the difference between these two terms. The last one is accuracy. It measures how well an instrument actually measures the true value. In reality, it will be very difficult for us to know the true value, which means it will be hard for us to know the accuracy unless the instrument is compared with a known standard. Usually there will be two errors related to inaccuracy measurement, systematic errors, and expected possible deviation from the true value. We have already defined a systematic error previously. Usually this type of error is related to the equipment, the measurement method, or the consistent offset during the measurement. The good things like we can apply some corrections to remove the systematic error so that we can make sure that our measurement is closer to the true values. The second one is the expected possible deviation for true value. This one is actually related to the accuracy of repeated measurement. In reality, we cannot guarantee that the instrument is able to measure a physical quantity perfectly at every time. Instead, we should state that based on the quality of the instrument, there's an expected accuracy range for the measurement. Usually, we will use the plus minus sign with a certain value to represent the possible deviations for the measurement to the true value. Okay, so that will be all about the lecture today. Thank you very much for your attention.